Really interested in people who are excited about the buffer interface, who can help me implement it. There's still a few things for a long time, something called a buffer interface. In Python 3K, the goal is to enhance it and make it a little more flexible to allow more objects to share their memory. NumPy, for example, many kinds of NumPy arrays couldn't really use the Python buffer interface because it wasn't capable enough to share the way NumPy laid out its memory. That's also true for the PIL. The way the PIL laid out its memory couldn't share its memory with NumPy very well through the old Python buffer interface. The goal of Python 3K buffer interface, which I hope to also backport to 2.6, that's the plan, is that it can extend the current buffer interface with more information. The current buffer interface only gives you a pointer to a memory and then how long it is, with a little bit of this sort of rarely used number of segments. I don't actually know of any object that uses that. The NumPy did for a while, but then because it wasn't quite a good match, we stopped doing that. The new buffer interface will have shape information, so you can have a multi-dimensional array or something you're thinking of as a 5-dimensional array, or a 5-dimensional chunk of memory. You're thinking about it that way. You want to communicate that to whoever's sharing the memory, that's how you're thinking of your object. You can communicate that to the buffer interface. You can communicate information about type. What is in the memory besides just bytes? If in fact the bytes are floating point to you, or they're a structured array of floating point with an integer and another string, you can communicate that through the new buffer interface as well. And then striding and offsets allow you to handle quite complicated memory layouts besides just a contiguous chunk of memory. You can handle memory that's arbitrarily strided in each dimension. You can handle memory that has offsets, somewhat like dynamic C multidimensional arrays do, with a pointer of offsets to other arrays. An array of pointers to other arrays. You can share memory that's laid out like that as well. So it's quite sophisticated in what can be shared, and we'll look into see a little bit of that. All of this, of course, is dependent on objects exporting and consuming that interface, just like it is for every one of the Python interfaces, the sequence, the mapping interface, the number interface. If the object doesn't support it, then it isn't there. But with the ability to share this way, I'm hoping that lots of objects will start sharing their memory, and we can get massive performance improvements for things like video libraries talking to NumPy arrays, or database views talking to NumPy arrays, or other kinds of large data moving applications. There is also additional feature that you can lock memory, so that you can, when you're consuming a memory interface, you can basically say to the object, I want your memory, don't change yourself while I'm doing my thing. That locking mechanism is also in place for the Python 3K buffer interface. Now, you can see probably that there's a lot of advanced functionality here, and sometimes, and you might wonder, where is the simple interface? How do I just share a simple pointer and a length? Fortunately, there are ways to do that. There's API calls as well as other kinds of calls to let you just do an easy sharing, as has been possible for a long time in Python. So why did I do this? What was itching? Well, in Python 3K, the essential core of the buffer interface is complete, and it's in Python 3K now. I still want to backport that to 2.6, and there's a few things that have to be fixed in Python 3K. So why did I do this piece? What was itching? Well, when I was involved in the numeric Python and numarray union, there was this need to have all of these different objects share their memory with each other, so the transition would be smooth for those who were still using numarray objects or numeric objects and wanted to start using NumPy objects, which is the new replacement. And so how are we going to do this? There was a real need to share memory in complicated, better ways than the Python buffer interface allowed. In addition, you look around the space of Python users and you see a lot more objects starting to use all kinds of memory. The PIL has its own way of using memory, and it's got large data that it's hanging onto, database views, all kinds of audio and video libraries are coming onto the scene where people are using memory. And from my perspective as a staunch NumPy user, I want to use their memory too, but because I want to do math on the memory that they have. And so I want it accessible to NumPy without having to copy to a string and then get the string back into NumPy and just doing these copies all over the place. I want to share memory in the same process. And graphics packages, WXPython, OpenGL, often need a texture, or they'll need a little piece of memory in order to display it on a screen, and I want that to come from a NumPy array. I don't want to have to go to a string and then to this other graphics context. So these are the things that we're itching and saying, I want this to be I want sharing to be more easy in Python, so how do we do this? One of the original ideas was to actually take NumPy and put it into Python. That's been made difficult by the fact that NumPy itself has been changing over the past couple of years, although it's stabilized now. And so that idea really didn't go very far. And so instead, we decided to do the Python buffer interface. And the Python 3K buffer interface really evolved from what's called the array interface, which we introduced in 2005 to share data between just NumPy arrays and numeric arrays and numarray arrays. This array interface just used two special attributes: array interface for a Python side way to get access to everybody's memory, and then a C side, a fast C side array struct, which would actually return a C object pointer to this array struct. You could have objects that must be extension modules in order to take advantage of the array struct interface. They could exchange memory, and I show a very small, it's very small text because I don't want you to spend too much time looking at that, but essentially that PyArray interface structure is what has become the Python 3K buffer structure that we'll see shortly. So the array interface has had a little bit of has a bit of success. NumPy, numeric, and numarray all support the array interface and can use that to exchange data seamlessly for people as they're transitioning from numarray and numeric to NumPy, which that transition has basically happened in almost every project that I'm aware of. There are still a few out there that rely on numeric. The PIL also uses the array interface. At least the 1.16 version uses the array interface, so it makes it very easy now. You can just say numpy.array, give it a PIL object, and all of a sudden you have a two-dimensional array of numbers corresponding to the image you just loaded, and you can two-dimensional or three-dimensional if it's a color image, and then you can just do math on that image and do all kinds of processes you'd like and store it back to a PIL array in order to use the input-output facilities to save as a PNG or to save as any other kind of image format. You can also, this little parentheses, there's a way that you can advertise. You can get C types to turn an integer into an arbitrary pointer to memory, and so it's a way to either be a very power user of Python or just to hose your system. It just depends on how brave you are and perhaps experienced. So PEP 3118, which defines the array interface, was launched after SciPy 2006. Guido gave a keynote there, and we had an opportunity to discuss things with him. And the idea of the array interface becoming the new buffer protocol was hatched at that point. Now, the reason it's taken sort of long to get it developed is because getting more people excited about it. I haven't been as good at getting a lot of people excited and helping me. And so it's sort of been up to how much time I've had. And that year, 2006, I had a job change and lots of things happened. So it's kind of moved a little bit slowly. But with the help of Carl Banks and Greg Ewing and others on the dev list, the PEP318 grew out of the array interface, and it added some really neat features beyond the array interface because of the input of those other people on the Py3K list. So, overview, and we're going to quickly just cover some of the what the buffer interface is. For more details, you can read the PEP. If you haven't shared memory of very complicated objects, there might be a little rough going in parts of it. But if you have any experience with C arrays or Fortran arrays or any kind of large memory constructs, you should see lots of things you've thought about. And in fact, if you see something that we've missed, like, hey, you really need to think about this, that's exactly the kind of feedback that's needed. And if it's not too big of a change, maybe we can actually fix things before Python 3.0 comes out. So that's why I'm really excited to give this talk and get people thinking about what we're doing in Python 3K. So basically, it redefines the TPS buffer function pointer table in the PyType object. So if you've seen how Python's type system works, there's this little place where objects can register how they behave as buffers. And currently, there's 4 functions in there, and we redefine that to contain only 2 functions and change what those functions are. And in addition, there's a Python side new Python object called a memory view object, which is basically a lot like a NumPy array, except without all the math. It's just the shape and type manipulations of a NumPy array. You can move bytes around. In fact, it's the first object in Python that will support multi-dimensional slicing. I think that's kind of cool because that's been around for a long time, but nothing distributed with Python actually supported multi-dimensional slicing. In addition, the other key piece is that it expands the struct module with additional character-based syntax to support more data types, more constructs. And then there's a few CAPI functions to keep common things simple. So the timeline, I've discussed a little bit already, is Python 3.0 alpha. It already contains this, but the memory view object needs some work. There's a couple of methods that need to be implemented still. And the struct module needs some work. And additionally, we'd like to backport this work to 2.6 in order to start getting people used to the new buffer interface and objects getting used to the new buffer interface. That's one of the difficulties in transitioning from 2 point to 3 point is extension modules. And anything using the buffer interface is going to be an extension module at this point. And so helping people start using the buffer interface in 2.6 is a critical piece of the success of this buffer interface, I believe. So, will anybody be working on it during PyCon? I will be working on it during PyCon. I'll stay for 2 days of the sprint, and anyone who wants to join me or get involved or be excited, I'd love to have you, and we can work on it. So, anyone interested in helping, please come to the sprints or contact me offline, and I'll get you up to speed, and we can do it together. So here's some of the gory details about what's going on. Here's the current pbuffer procs on the top. And it's transitioning to this new pybuffer procs, which just contains 2 function pointers, a get buffer and a release buffer. And the two, you notice in the top there's no release buffer, and there's no difference between a get buffer and a get write buffer. That's handled differently now. Here's the function call. Here's the function signature for get buffer call. It takes 3 arguments, the object being queried, a view structure to fill. On the next slide, we'll see what that view structure is. It's a new, basically, it's the Py3K interface structure. And then what kind of buffer is being requested. That's how some of the details of the locking are implemented, among other things. And it returns if a -1 if an error, and so forth. And then the other call that's way here at the bottom, you may not be able to see it very well, is the release buffer call. You call it with the same view structure that you passed in to the get buffer proc. And when you're done with the memory, you release it. Not every object will need to worry about that or will implement locking, and so not every object will implement a release buffer, and if it's not there, you don't have to call it. And that's handled through an API just like the current system, so you don't have to do that checking all the time. So here's the basic PyBuffer structure. Those familiar with the NumPy arrays will actually notice this looks a lot like the NumPy array header with a little bit of difference at the end to handle more arbitrary memory layouts. That sub-offsets at the end is rather interesting. And if you pick it up the sub-offsets in this talk, please come talk to me because it took me a little while to figure out what the sub-offset was doing. That was the brainchild of Carl Banks, which I was very impressed by. So the explanation for this is the buffer is the pointer to the memory. It's just a character pointer to the chunk of memory, to the start of the memory that's being shared. The length is the total number of bytes, although that can be pre-computed. It's nice to have it stored there also. Item size is the number of bytes per element. So that starts to get to the new concepts that are there. The first 2 is what previous buffer interface had, was just a pointer to memory and the length. Now we're starting to get to some of the new things that are added to the Python buffer interface. The number of bytes per element, so you can actually have a concept of the memory being divided into chunks that are the core P foundations of the memory, and then these chunks are just repeated. And so what is the item size of each of those chunks? So if you could think of sharing an array of floats, and each item is a float. Read-only, is the memory read-only or is it locked? The memory locking is handled by storing different values in read-only. How many dimensions does the user, the exporter of this buffer, think its memory is? This is really information added on top of this. All multidimensional arrays are always just one-dimensional. Well, it's not entirely true, actually, so let me be quiet about that. How many dimensions does the user think this memory is? And then the format is a string that is a struct-style syntax describing the memory. And if you've used the struct module, you can describe arbitrary memory layout with a few missing things that are added in the buffer interface. And that's essentially what that char star format is a string. Actually, I should use the word probably byte, a series of ASCII bytes, because string is becoming Unicode. It's a series of ASCII bytes that describes the struct. And then the shape is the size in each dimension. So the number of dimensions. And then the last 2, strides and sub-offsets, is how complicated memory layouts are used. Strides tells you how many bytes do I jump to get to the next element in a particular dimension. That's the concept of strided memory. If I have a one-dimensional array, or a one-dimensional sequence of bytes, and I have a stride of 16 and doubles in each of those elements, then I have to skip every other double, essentially, in order to get to what the exporter believes is his memory. So it's a way for you to have memory and then an exporter's ownership of some of that memory. And then the sub-offsets is how to get indirection. If the sub-offsets is greater than or equal to 0, actually it's less than equal to 0. So that's a mistake. If it's less than or equal to 0, then the value is actually not, the value stored is actually a pointer and has to be dereferenced in order to get to the next dimension. And so this is a way to handle the way some C arrays store their memory as an array of pointers to additional arrays. And you can actually share that through this Python buffer interface. So with the PyBuffer in Python 3K, it will be possible for the PIL and NumPy to share their memory for them to know each other. Now, how useful is that? You still have to, I mean, they don't map, and so you may have to have some conversions. But there could be, for example, another object that knows how to handle both kinds of memory and can seamlessly work with the memory that they're both sharing. So that's a potentially powerful use. But it is a relatively advanced use, so somebody has to be able to understand these concepts and make it work. And the flags are the way you tell what parts of the buffer interface am I actually using. Not everything is going to be as sophisticated. Some sharing of buffers will simply use the first two, the buffer, the pointer to the start of memory, and the length. And that's all it wants to share. And so the PyBuff simple says I'm only exporting simple, or I'm only wanting you to give me a simple interface if you can, and if you can't, raise an error. And so that's those are some of the flags. Highlighted in blue are the writable and the lock flags, which are how this buffer locking mechanism is implemented. Is a consumer of the interface will request an object using these flags and request it to lock itself. And we'll look at the next slide what the combination of those flags, how that works. Then some of these other flags say allow the consumer to ask the exporter of this interface, okay, I need you to give me format information, or I can handle strided information, I can handle sub-offsets. And the exporter, if it knows how to deal with those, will give back the appropriate interface. But it also allows an object to just expose a simple interface, and if a requester asks for a more complicated view of the memory, it can raise an error, or vice versa, if the consumer asks for a complicated view of the memory and the exporter can't, it can raise an error as well. And then there's a couple of, the simple flag at the bottom just allows you to request the object that, hey, I really need a contiguous chunk of memory. Can you do that for me? And give me just a contiguous chunk, or raise an error if you can't. So here's the memory locking mechanism. If neither flags are given, then you just want to read. The memory locking has to do with what other objects can do. If I'm a consumer of the buffer interface from an exporter, if I ask for your memory, what can other objects do before I've released? And that's what the locking mechanism is all about. So if I don't say anything, if I don't give any of these flags, then I want to read I'm only wanting to read your memory is essentially what I'm saying to the exporter. Other requests can do the same thing. They can come in and read and write, and there's no. So I'm assuming I can handle that situation. If I put a writable flag, then I actually want to be able to write to your memory as well. But other requests can also read and write. So there's potential there if you're in a threatening environment for problems if you're not careful. And so a lot of consumers may want to instead lock the memory. And there's ways to communicate, hey, I want to do a locked read. Other requests can also read, but they can't write because I don't want this memory changing while I'm dealing with it. And the final one is to do both lock and writable, which is an exclusive write. And this is really not very nice to other objects. It's basically saying that the exporter now no longer has the buffer interface. Is essentially what you're telling it. While I'm dealing with your data, tell everybody else you don't have any memory to share. Is kind of the request. So it's not very friendly and should be used, but is necessary sometimes in order to make sure that code works. And here's the function that explains sub-offsets. And there's another slide on the next page to show it a little bit as well. Pointer indirection. And the way this is implemented is there's actually an API call that you can give it a view and the indices you want to go into that array. So you can, if you have a multidimensional array, you can give it indices 1, 4, 5. I want to go to your 1, 4, 5 element in your multidimensional array. Give me the pointer to that piece of memory. And this get item pointer does that. And you can see what it does. It points to the start of the array, and then it adds strides corresponding to the indices passed in to increase the pointer. And then if there is a sub-offsets, it does a dereference. And there's an additional way you can do a dereference as well as add additional data. So that sub-offsets is a way to, allows you to dereference. Here's an example of sub-offsets in action. So if you had memory layout like this, where the buffer start of memory actually pointed to an array of additional pointers, and that's how your memory was laid out, you could still share that with this approach. So that's the concept of sub-offsets, and it would look like 0 and -1. Those are the sub-offsets you would use. Now there's examples in the PEP of this, but again, as I said, if you picked up on that in just this talk, please come talk to me. I'd love your help. It's actually, I was wrong. It is a positive number. So the fact that that's a 0 is why it's a dereference. Yeah, it's positive. The slide was correct. My statements were wrong. The slide is correct. I always have to go back and look at this function. So that's what that says. So yes. And here's some API calls that have been added. Getting the buffer. I'm going to go quickly over this so we can show the memory view object before question time. You can look at that later, and these slides will be available, so you can look at it there. And the PEP is available as well, and you can look at all this information there as well. The memory view object is essentially a simple wrapper around the PyBuffer structure. That's what it is. So it's a way for, in Python, for you to have this object that is a view into some other object's memory. And here's an example, and it's going to be pretty simple, only have a couple of methods, but allow setting and getting of bytes into that object with some attributes to describe what the person intended. So here's a simple example of how this might work. This code doesn't actually work entirely yet. The memory view object does exist, but there aren't that many 2D objects sharing their memory through the buffer interface. So you have to have some 2D object, let's say a PIL image, a grayscale image. You could print how many dimensions that memory view object has. And then here's an example of multidimensional setting of bytes. You could just, in Python, set bytes into this arbitrary data structure using slice syntax. And then you could get from mem format the struct syntax describing each element, and then pull out the bytes, or mem2list would use the struct style syntax to unpack the data and actually return to you this nested list of Python objects that has all the, so it's sort of this unpacking done in Python from bytes to Python objects. That's the idea of the toList. And then the bottom one shows how you might get a new memory view object from slices or pieces of the old memory as well. So I can imagine this functionality being really helpful to allow people to slice and dice memory for arbitrary objects and share it in various components of that memory with the other objects. The struct string syntax is the last piece, and you can see here a couple of the additions that have been made. There's a desire to be able to communicate bit field information as well as the platform bool, a long double, the UCS1, UCS2, and UCS4, a Python object pointer, a complex number, a pointer to a number, and a structure with T. And probably the best thing is look at an example of how that looks. So here's taking a C structure and how that would be translated to a Python struct syntax structure. You can see it's actually pretty close, just with slightly different nuances. So it's kind of the idea. You can get the idea that the point is to be able to share arbitrary C structure layout of memory with Python between objects. Here's an example using an array, so you can actually have the struct syntax support. I have an integer, and then I have a n-dimensional array as the second element of my structure. How do I share that? And that's possible here. I'm only using a 1D C array in that example because I don't want to confuse the difference between static and dynamic two-dimensional arrays in C. And it's just a pointer to memory that I'm talking about there. And it's the object that thinks of itself. So basically, the talk is over. Here's some implications. I'm excited for a standard way to share data between all of these different things that have large data in their memory. And in addition, we'll see what use people make of the NumPy-like multidimensional features and hopefully get a more powerful, improved struct C-types connection. So, but there's a lot of help wanted. So again, if you're excited to help, please join in and contact me, and I'll be available during the sprints. I'll be available all week. Come visit us at the Enthought booth. There's some cool things there to see, and you can, that's probably a good place to find me. And thanks for your attention.
Okay, so we've got some time for questions now.
That was easy. So why didn't you have the PyBuffer interface inherit from PyObject? Because if you did, then instead of having a separate release function, you could just call, deref on it. And then you could also introspect the object directly rather than having the PyMemory view wrapper around it.
Yeah, that's right. I mean, essentially, the PyMemory view is that thing, right? Is that PyObject enhanced PyBuffer. That went back and forth on the list. I mean, that was discussed, whether we should just have a PyObject be that thing that's shared. And I'm trying to remember what the good argument was. It was essentially that it looked more like the buffer interface if we didn't have a PyObject inserted in there. We didn't have to do reference counting of that PyObject. But I don't have a good answer for that. I mean, I think we'd have to look back at the list and see what it is that we decided. I'm forgetting. It was last year this discussion took place. So, yeah, Py3K. And I think it came up, and it was sort of decided against. We're sorry I don't have a better answer, but some of these things are just decisions that were made, right? Thank you. Is there a way to share a buffer between two different processes? Not directly, right? Because we don't have shared memory. I mean, you could certainly communicate that information some other way. Storing it to some inter-process communication could still do that. But you'd have to have shared memory really to share the memory between two processes. And currently there isn't a shared memory module that I know of in Python, although it would be a nice idea. A memmap? Oh, there is an mmap, and that's true. That's one way to share memory between processes. Yeah, that's true. That's true. It's a good idea. I mean, comments about how to make that more, improve that would be greatly appreciated. Good question. Other questions? Back here, in the back. Preventing starvation between rewriters, like stream kind of processing? Not really, no. Somebody could probably do something on top of this, but no. And if you have ideas about how we could improve things to make that easier, I'd love to hear them. Question? Yeah, great question. The question is there a reason the sub-offsets is done after the striding? And the reason is just that's the way Carl Banks suggested it. I mean, it could be done the other way, and it has implications both ways. I think I like this better. I've done some thinking about how to do a sliced memory view, and this one allows you to move the buffer instead of having to manipulate the strides. So I think I settled this was the right way to do it. But again, I have to think through that all the time, every time I think about it. So I guess the hope is we just have to do that once per object, then we don't have to think about it anymore, right? So thanks, good question. Very good question. All right. Well, I appreciate your attention.
All right. Thank you, Travis.